Good morning, everyone. I'm going to walk you through the notes today. So hopefully you can be listening to this with a headset of some sort. Um, but I'm just going to run you through the notes here real quick. These notes they are on class notebook. Feel free to pause this or rewatch it if I go too fast here at certain points. So today you guys are going to be learning about Newton's second law. And what Newton's second law tells us is that a body accelerates when acted upon by a net external force. So where the acceleration is proportional to the net force, inversely proportional to the mass, and it is in the direction at which the net force acts. And this gets written out in this equation here, net force equals mass times acceleration. And we'll talk more about this in just a moment here with the inversely and directly proportional and stuff like that. So this equation here is extremely important. It gets used throughout the rest of this class, so it's very important that you understand this. So the net force, remember this is the sum of the forces, the vector sum of those forces. So net force measured in newtons, and that's equal to the mass measured in kilograms and acceleration measured in meters per second squared, where the net force is always in the same direction as the acceleration. Whatever direction the net force is, the acceleration is in that direction. Whatever direction the acceleration is, the net force is in that direction as well. Now, to understand this equation a little bit better, what's oftentimes more useful is to actually solve for A. So to solve for A, we would divide both sides by the mass. So the mass would just come on over here, right? In which case then we get acceleration equals net force divided by mass. So we can see how do these variables affect the acceleration? Well, if I increase the net force, if the numerator gets bigger, then that's going to increase the acceleration. That should make sense, right? If you push on something harder, well, then it's going to accelerate faster. Okay? It's going to have more acceleration, I should say. Okay? And we can see that here in this simulation here, where if I say apply a force here, like so, 53 newtons, and the friction force is 53 newtons, well then what's the net force? Well, the net force would be 0, so we get no acceleration. Now, if I keep on pushing with more and more force, eventually I push with more force than the friction force, and I get a net force, in this case 82 newtons, and we can see my acceleration 1.64 meters per second squared. If I push with more force, well, then I get a larger net force, in which case then you notice my acceleration is larger. Right? You get that 5, whatever it was before this. Okay. And notice that if we go back here, that when the net force is to the right, the acceleration is to the right. It's moving to the right. The acceleration is to the right. So what happens? Well, it speeds up. Okay. Well, then if I let it go, well, now the friction force is only acting on it. So the net force is to the left. So the acceleration is to the left. Which way is it moving? Well, it's moving to the right. The acceleration is to the left. So what's happening? What's slowing down? Okay. So again, the acceleration is always in the direction of the net force, which could cause it to speed up or slow down. And again, the larger the net forces, the larger the acceleration, as we see here. What if we look at the mass term? Well, acceleration is equal to net force divided by the mass. So if the mass gets larger, then what happens to the acceleration? Well, we're dividing by a bigger number, which then gives us a smaller number. So that acceleration will get less. And again, this should kind of make sense here because you can imagine if you push on like a little pebble versus a big boulder, right? The pebble, which has a smaller mass, would have a larger acceleration, or vice versa. The boulder, which has a larger mass, would have a smaller acceleration. And we can see this here. So if I was to apply a force, a constant force here, let's get rid of friction now. So let's say we have a net force of 50 newtons to the right and our mass is 50 kilograms. Well, then we can see that we get an acceleration of 1 meter per second squared. And well, then, what if I increase this mass? So if I then say place a refrigerator on here, well, what happened to the acceleration? Well, it went down. Larger mass, less acceleration. And more specifically, what did it go down by? What multiple? Well, our mass went from 50 to 250, which is 5 times the mass. So we ended up going from, let's see here, an acceleration of 1 to zero point 0.2. So that's a fifth of the acceleration. So we got 5 times the mass, gives us a fifth of the acceleration. We can use proportional reasoning to help us out here to understand this relationship a bit better. So for example, if we triple the net force, what happens to the acceleration? Well, we can use the rule of one. So acceleration equals net force divided by mass. So we're tripling the net force and the mass is staying the same. So we plug in a one. So 3 divided by 1 is 3. So if we triple the net force, we get 3 times the acceleration. And this is our directly proportional. Whatever happens to the net force, same thing happens to the acceleration. If you triple the net force, you triple the acceleration. Okay. Now, what happens if we triple the mass? What happens to the acceleration? We'll use the rule of one again. So our net force, that's not changing this time. So we put in a 1. The mass is tripling, so we put in a 3. So the acceleration goes down by a factor of 3, or in other words, you get 1/3 of the acceleration if you triple the mass. And this is what's known as inversely proportional, because we can see that the acceleration is proportional to 1 over the mass. So whatever happens to the mass, kind of the opposite happens to the acceleration. So if the mass increases, the acceleration decreases by that same multiple, in this case, by 3, or you get 1/3 of the acceleration. If the mass was to go down, then what happens? So if we have, say, half the mass, what happens to the acceleration? We'll use the rule of one again. Acceleration equals net force over mass. Net force isn't changing. Plug in a 1. Our mass, we get a half of it. So 1 divided by 1/2, well, that's 2. So if we have 1/2 the mass, we get double the acceleration. So by decreasing the mass by a factor of 2, we increase the acceleration by a factor of 2, inversely proportional. Okay. So now let's look at a graph of force versus acceleration. And you guys may have made a graph like this on the PhET lab that you guys did the other day here. So to graph net force versus acceleration, so we got net force on the y-axis and acceleration on the x-axis. And if we just make a sketch of this, well, first we could plot a point here at 0, 0, because if we have zero acceleration, then what has to be the net force? Well, it also has to be 0. And then in order to have a larger acceleration, what do we need? Well, we would need a larger net force. So as that acceleration increases, we need a larger and larger net force. So we get a directly proportional relationship here, a linear line increasing like we see here. Okay. Now, I did this for 2 lines here, one that has greater mass and less mass here, to understand what the slope of this graph represents. So to see this, we could model this line using our equation y equals mx plus b, where the y-intercept is 0 here. And well, what's on my y-axis? Well, that's the net force. What's on my x-axis? Well, that's the acceleration. And the slope, it would be, well, what's in front of a? Well, in our net force equation, the mass is in front of a. So we get net force equals mass times acceleration. So the mass represents the slope of this line here. So we can see the one with the greater slope is the one with the greater mass. And we can see, well, does that make sense? Well, for the same net force, which one is going to have a greater acceleration? Well, the one with less mass would have a greater acceleration for the same net force, which is why we have a point over here, versus the one with greater mass for the same net force, you'd have less acceleration, so you'd have a point right here. So should make some sense here. Now, second law problems, there's a strategy to solving these that we can systematically use. So first, as always, what do? We draw a free body diagram, label our knowns, our forces, our unknowns, etc. Then we set up our second law equations in each dimension for each object. So we'd say the net force in the x direction equals the mass times the acceleration in the x direction, and or the net force in the y direction equals the mass times the acceleration in the y direction. And then we can solve the equation for the unknowns. So what does this look like? And again, if I'm going too fast here, which I probably am, feel free to pause it, write stuff down, and then keep going. Okay, so let's look at an example. If we have a net force of 50 newtons acting at a 30-degree angle north of east acts on a 25 kilogram boat. Find the acceleration to the east and the acceleration to the north. So first I can draw my diagram here. Here's my boat. And our north direction and east direction, we have a net force of 50 newtons here, 50 newtons at a 30-degree angle north of east. Okay. So what we could do is we could write out our equation for each direction. So if I want to know what's the acceleration to the east, well, that's in my x direction. So the net force in the x direction equals mass times acceleration in the x direction. And if I define to the right as positive here, well, then what I can do is I can figure out, well, how much this net force is acting to the east. Well, I can break this up into its components. So I draw an arrow to the right, an arrow up here, and this would be the adjacent side of this right triangle. So the net force in the x direction would be the hypotenuse, 50 newtons, times the cosine of 30. Excuse me. Okay, so then if I plug that in for the net force in the x direction, 50 cosine of 30 is equal to the mass of 25 kilograms times the acceleration to the in the x direction. Divide both sides by 25 to get 1.73 meters per second squared to the east. And well, we can do the same thing for the y direction. So we can write net force in the y direction equals mass times acceleration in the y direction. And well, what component of the net force acting in the y direction? Well, that's the opposite side here, so that's sine. So we have 50 times sine of 30 is equal to 25 times the acceleration in the y direction. Divide both sides by 25 to get 1 meter per second squared to the north. Okay. Now, what if we want to know what is the resultant acceleration? Well, we can put these accelerations together. So we have 1 meter per second squared to the north up here and 1.73 to the east to the right here. So then we can solve for the hypotenuse here by using the Pythagorean theorem. And square root of 1 squared plus 1.73 squared gives us 2 meters per second squared. And we can solve for this angle by taking the inverse tangent to get 30 degrees north of east. Okay. Now, could you figure out another way to get this 2 meters per second squared? So if you'd like, pause it and think about how else could we have gotten this 2 meters per second squared. Okay. So another way that we could have gotten it is just by looking at the resultant net force, because the acceleration is in what direction? Well, it's in the same direction as the net force. So if we take the net force, well, that's equal to the mass times the acceleration. So that would be 50 newtons as our net force is equal to the mass 25 times A. So divide both sides by 25 to get 2 meters per second squared. Now, one thing that we went over in our kinematics unit is we checked this out. We said, so why do all objects fall with the same acceleration regardless of mass? So in our previous unit, we saw that, hey, if I took a really large, massive object, like a bowling ball and like a tennis ball, well, if we drop them, they have the same acceleration. Everything on Earth has a negative 9.8 meters per second squared acceleration. Okay. So why does that not matter what their mass is? Well, we can use Newton's law, second law, to help us understand that. So if I have an object in free fall, well, what force is acting on it? Well, it's just its weight, mg. And if I define down as negative, well, then we can say the net force in the y direction is equal to the mass times the acceleration in the y direction. So the only force acting on it is mg in the negative direction. So we have negative mg equals mass times acceleration. Well, notice, what do both of these terms have? Well, they both have mass, so we could divide both sides by mass, canceling them out, which then says, hey, well, that means the acceleration in the y direction is equal to negative g, just the acceleration due to gravity here, which would be our 9.8 on Earth. Okay, so this is kind of a mathematical explanation. So what about a more conceptual explanation? Well, notice, right, if we have more mass, this mass here, more mass, well, then that means that we have more weight. mg is the weight, so we have more weight, which means we have more net force. And typically, as we talked about before, right, if you have more net force, what happens to the acceleration? We have more acceleration. Okay? But there's another mass. There is the inertia, right? There's the inertial mass. So if we have more mass, well, then then we have more inertia. And if we have more inertia, more inertial mass, well, then we have less acceleration because it takes more force in order to create that same acceleration, okay, on a more massive object. So more mass, more inertia, less acceleration, more mass, more weight, more net force, more acceleration. And these two things kind of cancel each other out, um, which ends up having no change in acceleration, regardless of the mass. Okay. All right, let's look at another example here. Let's say we have a 50 kilogram crate is pushed with a net force, or sorry, with just a force, not a net force, with a force of 118 newtons. It is on a rough surface and friction acts with a force of 68 newtons while it is in motion. What is its acceleration? So we draw our free body diagram here, right? So we have our crate, it is on our surface here. So what forces are acting on it? Well, we've got the applied force. I just labeled this as F1, equal to 118 newtons. And then if it's, say, moving to the right here, well, then that friction force would be in the opposite direction of the motion, being 68 newtons. Okay. And then we also have the surface pushing upward with the normal force and the weight downward, mg. So to figure out the acceleration, well, it's going to be accelerating in the x direction. So we just have to use the x component here. Net force in the x direction equals mass times the acceleration in the x direction. And then write an expression for the net force in the x direction. So what forces are acting in our x direction here? Well, we've got F1 to the right. And if I define that as my positive direction here, positive direction to the right here, then we'd have F1, and then friction would be in my negative direction here. So we'd subtract the friction force here equals ma. So then if we plug in our numbers, F1 118 minus friction 68 gives us a net force of 50 newtons, which is equal to 50 kilograms times acceleration. Divide both sides by 50 to get our acceleration of 1 meter per second squared. Okay. All right, now let's do a little bit of a tougher one here. So let's say we have a 21 kilogram lawnmower is pushed with a 250 Newton force along the handle that is angled 54 degrees above the horizontal, causing the mower to accelerate at 3 meters per second squared. What is the friction force and the normal force that acts on the mower? And how far will you push it after 4 seconds if you start from rest? Okay, so let's look at a diagram here because this maybe is a little bit hard to understand from this, just the words here. So the idea is we have our lawnmower, right? And you have your lawnmower with your handle here. And the idea is in this problem, we're going to kind of maybe push on it, maybe a little weird. We're not going to push it just to the right. We're actually going to push kind of along the handle, as it says here. So we're going to push kind of parallel to the handle into the ground a little bit. So to the right and down. We're going to be pushing with 250 newtons at an angle of 54 degrees with the handle. And that's going to cause it to accelerate to the right here at 3 meters per second squared. Okay. So what we're going to do is draw a free body diagram here. So over here we have our free body diagram. So what forces? Well, first we have F push at 54 degrees. So why is this angle 54? Well, remember from geometry here, if we have a line here and a line here, this angle is congruent to this angle because of what? That's right, vertical angles are congruent here. So this angle here would be 54 degrees. And then we also have the friction force acting opposing the direction of the movement here. So if it's moving to the right, friction would be to the left. And then we have normal force upward and mg downwards here. Okay. Then what we can do is write out our equation. So for the x direction, net force in the x direction equals mass times acceleration in the x direction. So what force is acting in the x direction? Well, we've got the friction force to the left, but then we also have F push that we can break into its components. So it has a component to the right of F push cosine of 54, the adjacent side. So we take the force in my positive direction to the right minus the friction force equals ma. So then we plug in our numbers here. So 250 newtons for the F push here times cosine of 54 minus the friction force equals ma. And we were told the acceleration was 3 meters per second squared, and it's to the right here, so it's positive. Okay. And then we can plug our numbers into our calculator here, get 146.95 minus friction force equals 63. Subtract that to both sides here to get negative F equals negative 83.95, divide by negative 1 to get our friction force of 83.95 newtons to the left here. Okay. Now, we'd also like to know what is the normal force. So to get the normal force, we have to look at what direction. Well, it's in my y direction, so I've got to look at my y direction. So we can say the net force in the y direction equals mass times the acceleration in the y direction. And well, what is the acceleration in the y direction? Well, our lawnmower is not going to accelerate up or down at all. It's just going to be accelerating to the right. All right, so it's not going to like accelerate into the ground, or it's not going to be like lifted off the ground at all, right? So we can say the acceleration in the y direction is 0, which means we're basically using Newton's first law, right? Net force in the y direction equals 0. Okay, so then, well, what forces are acting in the y direction? So in the y direction, I highlighted them in green here, right? We have the normal force up. So if I define up as positive, then we have normal force up is positive. We have mg down, so that's negative, so minus mg. And then we have a component of the pushing force acting downward as well. So we have to subtract F push sine of 54, the opposite side here, so sine, right? So we can put that over here, normal force minus mg minus F push sine of 54 equals 0. So to solve for the normal force, we could add both of these to the other side here, right? But adding them. So it brings it to the other side of my equation here, making them positive. And then we just plug in the numbers here. And then plug it in your calculator to get 408.05 newtons. One thing to be careful of is we have an n here and an n here. Keep in mind that this is the normal force and this is the unit newtons. All right, so this is the variable normal force. This is the unit newtons. Okay. All right, so then the next part says, how far will you push it after 4 seconds if you start from rest? Okay, well, that sounds like kinematics to me, right? So we know the acceleration. So how far is it going to move after 4 seconds? Well, if it starts from rest, so it starts from an initial velocity of 0. We want to know what's the displacement. So we can write out our 5 kinematic variables that we use for constant acceleration. We don't know the displacement. We know the acceleration, time of 4 seconds, initial velocity 0. So which equation has these 3 variables? Well, that's our equation here. Plug in our numbers to get 24 meters. Okay. So I know I went through that pretty quickly, so you may need to, again, make sure you guys kind of listen to it maybe a couple times here. And I'll also put another video that if you want to see some more just examples or another person talk about this, he explains it pretty similar to me, but the way he shows his work is a little bit different. I do want you guys to show your work like this, though. Always start with the equation and then substitute in the variables, like so, right, for those net forces or for those forces. And then solve from there, whether you're solving for a variable or you're solving for a variable being like an unknown force, right? Or if you're solving for an acceleration. So that way the setup is the same every single time, right? You're starting with net force equals ma for direction, plug in those, an expression for the net force, and then once you've done that, then you can plug in the numbers and solve for whatever variable, use some algebra. Okay. So I hope that was helpful, you guys, and hopefully I will be back on Thursday. So make sure you guys try out the homework, check the answers, the homework being 2.3. Have a good day, guys.